Welcome back to Pocket Run. Hey, where are you going? It's just math. Don't run away. Hey. Oh, well.
Okay, we're going to do rate of decay problems and rate of decay, also other interest rate problems. These are just some examples of where you can see exponential functions and natural log functions being used in the real world. Okay, so for the majority of these problems in this book, the formula, the rate of decay formula or your interest rate formula will be given to you. Okay, so here's some information that has been given to us. The half-life of iodine, if you've taken chemistry, iodine 131, that is an isotope of iodine. Okay, so the half-life of iodine is 8 days. What that is the time it takes for 1/2 of the substance to decay or change into another kind of matter. They're explaining what the definition or what the term half-life means. Okay, so they actually give you the decay formula. This means Q of t. This is a function. This does not mean Q times t. Q of t, this equals IE to the negative KT. This is an exponential function. Anytime you have e to some exponent, it's considered an exponential function. Then they're telling you what all these letters represent. I represents the initial amount of the substance, the initial amount. T is the time in days. K is the decay constant. That will always usually be given to you as well. For iodine 131, K is 0.087. Okay? So I represents the initial amount of, in this case, iodine 131. Q of T represents the amount of iodine 131 we will have after a certain amount of time. After a certain amount of days, how much of it will we have? Okay? So in 22C11, they're actually asking you how much iodine will be left after 12 days. So we're starting with this formula, Q of T, which this represents how much iodine I'm going to have after 11 days. That's what this whole symbol represents. IE to the negative KT. Okay? Well, we've been given the decay constant that was given to us up in the information. So for iodine 131, that is 0.087. So that is something that we know. We know that. So we're asking how much iodine would be left after 12 days. That's what this T represents. How much do we have after how much time? Okay, in this case, 12 days. So we know T. So E is 2.718. That doesn't change. Okay, it's a constant. I, what does I represent? It represents the initial amount of the substance. So the initial amount of iodine. So we go back to the problem, all the information that we were given. Alright, so we need to know the initial amount of iodine. In problem 22C10, it says how much of 6 grams of iodine 131 will remain after 10 days. And they work that out for you. So we're told in 22C10 that the initial amount of iodine is 6 grams. Okay, so we know that as well. So the only thing that we don't know is how much iodine is left after the 12 days that we're looking for. Okay, so what we're wanting to know is how much iodine after 12 days. This doesn't mean Q times 12, it just means Q of 12, the amount after 12 days. Okay, so we can start filling in what we know. We know the initial amount is 6 grams times e to the negative, and don't forget your negative here, and then K is 0.087 times the amount we're trying to find is after 12 days. Okay, so that's after 12 days. Okay, I didn't write all my units in here. We aren't told what the units for this constant are, but if we're looking for an amount of iodine, what should our units be? Our units should be grams because we're looking for an amount. Okay, so PEMDAS says we do our exponents first. Don't multiply first. Do e to this first. So we're doing our exponents. So 6 times e to the, I'm going to multiply these two numbers together first. Negative 0.087 times 12 is negative 1.044. So I need to get e to the negative 1.044 first before multiplying it to 6. What does this mean? In order to make that exponent positive, it means you change the place of the base. So this is 6 times 1 over e to the 1.044. So you're doing e to the 1.044, and then you're doing the reciprocal of that, or 1 divided by that. So this will be 6 times 0.352. So 6 times that. Rounding it, I got 2.11 days, and I don't remember if they went to one decimal or to a whole number, so I got 2.11. I'm sorry, units aren't days. This is how much iodine is left, so grams. 2.11. I'm taking mine to 2 decimal places. So we started with 6 grams of iodine, and this rate of decay, it's decaying. So you need to make sure your answers make sense. So since it's decaying, it means your final answer should be smaller. If you start with 6 grams, then after 12 days of decaying, you have 2.11 grams left. So make sure your answers make sense. Okay, now looking at 22C12, it's still connected to the same problem. This question is asking how many days would it take for only 1 gram of iodine to remain. Okay, so it's still connected to the same problem, so we're still using the same formula. So you're still using this formula that they give you, that the amount after a certain amount of time is I e to the negative kt. Your rate of decay won't change. That will always stay the same for iodine 131, so you know that. How many days? That's what we're looking for. How many days? So we're looking for our time. The t is what we don't know. Okay? So we still know our initial amount. That didn't change at all. Okay? So our initial amount was still 6 grams. So, and then it says, how many days would it take for only 1 gram of iodine to remain? So we're trying to find out after how many days. We started with 6 grams, and now we're going to end up with 1 gram. How many days or how much time did that take? So this 1 gram is this new amount. Okay, so we know that as well. You should know everything except for one thing. You should only have one unknown because we have one equation. Okay, so now let's start plugging in what we know. This is our new amount after so many days or so much time. That's what we're trying to find, the time. So that was 1 gram. I'm not even going to write in my units. I'm looking for time, and right now this is days. And according to our formula, this t is represented in days. Okay, so 1 equals our initial amount was 6 grams. E to the negative, our rate constant was 0.087 t. That's my unknown. That's what I don't know. So my unknown is in my exponent. What do I do if my unknown is in my exponent? How do I get the unknown out of the exponent? You take the natural log of both sides. Okay? First, before we do that, I'm going to tell you to get rid of this constant, this 6 in front of here. Okay? It's easier to get rid of any coefficients in front of the e before taking the natural log of both sides. Okay, so 6 is being multiplied to this, so to get rid of it, we divide it away. Okay, 1/6. I can put it into a decimal or I can leave it as a fraction. Okay, so now I have 1/6 equals e to the negative 0.087 t. So now I'm going to take the natural log of both sides. Law of logs say I can take my exponents and bring them down in front. Okay, so I have natural log of 1/6 equals negative, don't lose your negative, 0.087 t natural log of e. What is natural log of e? Natural log of e is 1, so that basically becomes a 1. Anything times 1 is itself. So now we can say, I'm going to turn this natural log of 1/6 into a decimal. And that becomes negative 1.79. I basically did 1 divided by 6, then took the natural log of that. Okay, that was negative 1.79 equals negative 0.087 t, because that was 1. How do I solve for t? Divide both sides by this. The fact that we're solving for time tells us it should be a positive number. You should never get a negative number for time. Okay, we have a negative divided by negative. That will be a positive number. That is a good thing. Always make sure your answers make sense. So dividing that out, t comes out to 20.57 days. Again, I'm not sure if they're rounding to the whole days or if they're leaving it in decimal, but I'm going to leave it in decimal because that's more accurate. So basically, if you start with 6 grams of iodine, iodine 131, and then you leave it for 20.5 days decaying, after 20.5 days, you're going to end up with 1 gram of iodine.